Okay, so I suppose that you can see my screen, right? Can you confirm that? Hmm?
Yes, sir. Yes.
Okay, thank you. So we need to say a few things about these properties, and I um, I want you to be able to connect some of these properties to Fourier series as well. So we'll start very simple, and let's say we begin not by properties, but first we start with a particular pair. So let's focus on this pair, this one, right? So what does this tell? That if the time domain signal is a constant, so if you plot this, you will get a constant. This is time, and you have a constant signal. You have a constant signal 1, right? So in the frequency domain, so when you actually transform it, continuous time Fourier transform. So here you'll get, this is now the frequency. So this was the time, this was the frequency. And what you get here is that you have at 0, you have an, I need to fully draw the vertical axis, and then we indicate this delta, Dirac delta. What do I write on top of this? Can you recall? When we draw this vertical arrow for the Dirac delta, we write something on top of it. What must I write here? Hmm?
Delta of omega.
No, but that is obvious, bro. Yeah, I mean, you can write x of t, and
K of delta of omega.
yeah, so this is 2 pi. Actually, the constant is multiplying, yeah. Whatever constant you multiply, that will be the area. So you just write the area, 2 pi delta of omega, not just delta of omega, okay? So this is what you read uh, from the property table. But there is more, okay? And I want you to write it just below it so that you can see. So if I have a transform x of omega, right? How do I get back my time domain signal to reconstruct it? Do you recall that? I have to integrate this, multiplying, this time it's positive j omega t d omega, and then 1 over 2 pi, right? So if I try the same thing with this pair, what do I get? Just apply the same thing. So I should get on the left side, what should I get here on the left side? Hmm? 1, right? Well, it's a constant signal. And it's 1 over 2 pi. And this is actually from minus infinity to plus infinity. From minus infinity to plus infinity. And then for x of omega, I write 2 pi delta of omega. And then So let's simplify this. And now I want you to be able to interpret this thing. So 2 pi cancels out, right? And I'm left with the integral j omega t d omega. And of course, when we evaluate this integral, we get 1. How will you interpret this? So how do you interpret this thing? If you can interpret this thing, then you should be able to interpret this thing. So let's recall, I'm now using different color, that the claim here is that any time domain signal, if it satisfies certain conditions, of course, yeah, it must be finite energy and those Dirichlet conditions. Everyone remember those conditions, Dirichlet conditions. Otherwise, this Fourier transform doesn't work. So, um, or if otherwise, we have to use this generalized transform. Yeah, there is always an option, generalized transform. So I can reconstruct that signal from some basic signals, and those basic signals are actually these exponentials. So I can use exponentials to construct my signal, not as a sum, just as we did it in Fourier series, but as an integral. So I can express any time domain signal as an integral in which I'll be using exponentials, complex exponentials, and each exponential will have certain weight. That weight is what we know by the name Fourier transform, and that transform, because it's an integral and not a sum, that coefficient, weighting factor, we cannot call it the amplitude, but we can call it the density of the frequency components, because then you have to multiply it by d omega. So, I mean, you can imagine a tiny interval d omega around, let's say, some value omega, and in that interval, you say, okay, in that tiny interval, all the frequencies will have this contribution x of omega times d omega, and then we have to gather all these frequencies and I get my original signal. So if I keep that interpretation in mind, what this tells me, that if I want to construct a constant signal, and if I want to construct it from the exponentials, although this integral is from minus infinity to infinity, but if you look at the graph, I don't need any frequency other than 0. So 0 is the only frequency which I will have to use in this integration, right? All the other frequencies that disappear, that they are not needed. So how can you explain this behavior? Why is this so strange that we just have one frequency? Here the integral says that you may need all the frequencies, but literally you need only one frequency. So what will be your explanation for that thing?
सर कांस्टेंट सिग्नल है तो फिर उसकी फ्रीक्वेंसी नहीं होगी
तो एक फ्रीक्वेंसी होगी और वो जीरो होगी, right? And this also raises another question, that how do you define a frequency? Can you recall how do we define a frequency? So what will be your definition of the frequency of a sinusoid or of a signal if it is periodic? We also know that frequency is only attached to periodic signals, right? So
ये
what is the frequency of a periodic signal? We can either write f or omega. What's the definition? We
One
either
by
say
time period
1 over time period or 2 pi over.
pi by t.
What is wrong with this definition? We use it every time, but there is something terribly wrong with this. And at this point in this course, you must be able to tell me why. What is wrong? I wouldn't expect it in a previous course, but in this course, you have learned enough to tell me what is wrong with this definition. This is not complete, okay?
The phase, sir.
No, you don't need phase
Is-
for this. You don't need the phase for this. So in this course, what you have learned that most of these equations, they have a cage, they have a corner case. So this, let me write this down and you are going to then complete it yourself. Okay. So this 1 over t is only when the signal is
T is
varying.
not equal
If
to 0.
if it's a varying signal. Yeah. So if it is not a constant, if yeah, I would say not constant. Yeah. So if it is a constant signal, then you know when we were defining periodicity, what do you mean by a periodic signal? Yeah? What do you mean by periodic signal? Right? If you have a signal X, if it is periodic, yeah, for every time t, right, it must be possible that you shift the graph by some amount and it must not change. Do you remember this definition? And then
Yes.
the smallest of all such amounts is what we mean by the period, the fundamental
Fun-
period. So if we have a constant signal, is a constant signal periodic? Try to recall that. Try to plot it, okay? I just plot a constant signal. Is it periodic?
yes, sir.
Yeah, because I can shift it and it won't change. But can I compute its period?
No, sir.
Yeah, because there is no unique period. Yeah, the period by definition has to be the smallest and positive. The condition is that this t must be positive and it must be the smallest of all periods. We can't find the smallest period here. So that's the problem with constant signals. They are periodic, but they don't have um, they have periods, but they don't have the fundamental period, and that's what we mean by t. And this t is not just any period; it has to be the fundamental period, right? So now, what do? We are stuck here. We cannot use this formula to write the frequency of a constant signal, but we know the answer. What is the answer here? Tell me. Sometimes we know the answer without using a formula.
One.
Is the frequency of a constant signal 1?
0.
0. To write 0 here, you don't need any formula. Okay? 0 means it doesn't vary. Yeah, it has no variation. You get it now? So you are not supposed to use this formula, you are supposed to use this formula. Okay? So we know that the constant signal has frequency 0, right? And that is what is confirmed by this property, which I just explained here. The constant signal only needs 0 frequency, right? But there is one thing which is uncomfortable here, that why do we see this delta, Dirac delta? You know, it's a generalized function. It's a weird thing. So we would like a simple explanation as well. So like this concept was very simple. Yeah, we know the frequency is 0. So I want you to think about this same problem in Fourier series. And so how will you go about this in a Fourier series context? I will again start with this constant signal, right? So now if I start with a constant signal, sorry, 1. So I want to work out the Fourier series. So how do we go about it? What will be the Fourier coefficients here? Ck. What will be Ck for this? Can you recall? It was,
It will be infinite.
you had this formula, right? What was the formula?
1 over t. 1 over t is 0.
Yeah, any period, yeah. And then
X of t e की power minus iota omega t.
minus, I think it was k omega naught, right?
Yes.
T dt. So what do we do here? We know t is not defined. So how do we solve this problem? Hmm? Just like we knew the answer here without using any computation, I want you to be able to tell me this without using this integral, because this integral doesn't work, yeah? But you know something. I told you this is the importance of knowing the meaning of something. If you are only focusing on computation, then you will always have this problem, yeah? You will not know what to do in these corner cases. So apart from this computation, what is the meaning of this integral? I told you once. Because we know
I
we use this for for periodic signals, yeah. So you are actually integrating something, and then you are over some period, and then you are dividing it. So because you are doing it for a specific time, it is just the average value, right? The average value over one period, yeah, over one. Actually, you don't need to say over one period. Average value is average value. You can use any period. You can even replace this with 2t, yeah, and it will still work, right? So as far as the average value is concerned, so you know the average value of this constant signal. Tell me. You don't need this integral for that. What is the average value of a constant signal?
The amplitude
mhm.
of this constant.
Same value, the same value. You use the word average only when something varies. When it doesn't vary, that's the same value. Let's say you get 50 marks in every course, right? Or let's say everyone in the class got 50 marks. So what is the average of that class? 50. You don't need to compute it. So now ck is what? It is
It is
1.
1.
it is 1, but only when k is, it's not 1 for every k. It is 1 only for k is equal to, tell me. You will get this for only k is equal to 0, because that's the zeroth coefficient. It's a constant, zero frequency. For all the other values, right? You don't need any sinusoid. You get this now? What is this
Yes.
function? What is this function? You know the name for this function already.
Delta.
It is the discrete time delta, which is we call the canonical delta. See? So we just write it as delta. Um, yeah, delta. It's just delta. You write it here, delta k, right? And some people write k comma 0 because it's at 0. And if you want to plot it, it will be like this. K at 0, it has a value of 1, and everywhere else it is 0, right? Now let's look at this plot in Fourier series and at this plot. And what did we get in? Let's switch back to Fourier transform. Okay. In Fourier transform, this signal, again, this constant signal and the frequency domain. What did we get there? Right? Although we have this continuous time delta here with infinite amplitude and area 2 pi, here we have a finite, but they are related. Can you tell me in which way they are related? So they're actually telling the same story, despite the fact that one is a finite quantity and the other is infinite. The reason for this is what I told you in the beginning. When we developed Fourier transform from Fourier series, we did something, right? We knew that Fourier series only works for periodic signals, right? But we pretended that it's, and Fourier transform is usually used for aperiodic. We started with a period t and then we let the period approach infinity. And in so doing, what happened is that coefficient ck, right, that disappeared, that became zero. And to avoid this zero, seeing the zero every time, what we did is that ck, we divided that ck by some frequency, right? Omega. I think there was this 2 pi as well. So it was actually the density of those coefficients. You can think of it as not the coefficient because all the coefficients become zero, but coefficient density. And by density means per unit frequency interval. So you can now make sense of this. The coefficients are zero everywhere, and it is non-zero only at one point, right? So if you now look at the density and this tiny interval, if you now turn this to a frequency axis, and this tiny interval of zero, almost zero width, it suddenly changes. The coefficient changes from 0 to 1 and then comes back. So what is the density at 0? What is the density of a quantity which changes within no width from 0 to 1? It's infinite, right? Infinite density. You get this point? That's why you get this delta. So one more example. I mean, if you have understood. Yes, so there was a question.
सर ये रिपीट करते हैं डेंसिटी इनफाइनाइट वाला.
Yeah, so let's say let's me give you a simple example. Let's say you have this you imagine your classroom and you are sitting in these rows and columns, right? And I have drawn these so that you can imagine. Let's say there is one seat here. Sorry. Let's say there is one seat here where someone is sitting, and one seat or some tables or whatever. There are objects in that room. Okay. Although I'm drawing this uh, square, but imagine that it's just one point. Yeah. So it's just at this one point there is something. There is some solid body. Yeah. And then there is another object at this. I mean, it's almost zero volume. It's a very tiny region, but you have something heavy. Yeah. So, and now if I'm asking you, if you're dealing with masses, with mass, so you will say, what is the mass here? Everywhere else, the mass is zero, right? But here the mass changes suddenly, right? So mass is non-zero only at these points. Everywhere else the mass is zero, right? So if you are looking for the mass, you have a simple picture. Yeah, it is either zero or non-zero. But if I now ask you what is the density, which is mass, rate of change of mass with respect to volume. So what is the density here? Everywhere else? Hmm? When mass is zero, density is also zero, right? But what is the density here at this point?
Mass per unit.
Yeah, so mass changes from zero to non-zero within zero volume. So this will be, so density will actually be zero everywhere except at those points when it will be infinity, right? Whenever something changes within a zero interval, it becomes infinite. That's the main idea of this Dirac delta. Dirac delta captures things that change suddenly, right? And now I'll give you one more example, and this will actually, I don't think you should need any other example. You already know the connection between delta and unit step. So how do you plot unit step function? You have time, you have this y-axis, and how do you plot it? It is 0, 0, and suddenly it changes to 1. Okay, so now tell me, this is your u of t. Now differentiate this. I will say I want you to differentiate this. So when you differentiate this, what is the derivative in this region? Tell me. It doesn't change, yeah? So the derivative was also 0. What is the derivative in this region? It is also 0. What is the derivative in this region? Hmm?
Manu.
Tell me.
Infinite.
Infinite. Yeah. But not just infinite, because there are many types of infinity. It is Dirac delta. Why? Because we also know that it changes from 0 to 1. So here you are differentiating. If you are integrating, the integral we know will be 1, yeah? The change will be 1. So because the integral is 1, so it is 1 delta. It is not 2 delta or 3 delta or half delta. Yeah? So you actually have developed the concept of this this, you can think of it as the generalized derivative, right? It is not the derivative of your calculus, because in calculus this derivative doesn't exist. This function is not differentiable. But we are using this generalized function, yeah, generalized transform, all these things. So the generalized derivative of any jump will be a delta, right? So let's get back to that table of pairs and see some more interesting things. And now I'm now removing all this. Okay, so we discovered last time that I can go from this property, sorry, from this pair to this pair simply by modulation, right? I just multiply this. So if I apply modulation, I get this property and get this shift. And I can then combine these two, right? I can combine this with its time reversed version, right? And then add and divide by 2, and then I can get this one. So cosine and sine. So let's write these on the other side. So I'll now write cosine omega naught t. If somebody can remember it, then tell me there, right? So I want to write this, that if I have cosine omega naught, t omega naught can be any fixed number. And if I take the continuous time Fourier transform, what I get here is pi times. This pi actually should have been 2 pi, but because of this division divide by 2, we have 1 pi. And it is delta of omega minus omega naught plus delta of omega plus omega naught. Remember, this shift is because of that modulation by this frequency, this complex exponential, and this shift is because of the other one, right? So one will introduce a shift to the right and one will introduce a shift to the left. Is this clear so far? Right? And
Yes, sir.
now let's look at the plots. How will the plot look like? In the time domain, I know how to plot this, right? So a typical plot will look like this. I'm never proud of my plotting skill, but I'll still try. Okay, so what is the first thing you can say about this signal? It is a periodic signal with just one frequency, and that frequency is omega naught, right? The angular frequency. There is no other frequency in this signal. Yeah. So it means that in the Fourier transform, if I now plot this thing, I should see the same picture. How many frequencies do you expect in the Fourier transform? Tell me. Just one frequency, right? This is one frequency. So now plot this one. One Dirac delta is at omega naught, this one, right? And the other one is at minus omega naught. And this will be of strength pi, the area pi, and this will be the area pi. So why do we see two frequencies when I said that you just need one frequency? Can you explain that? When I said one frequency, I was talking about real signals, yeah? We know Fourier transform and continuous time Fourier series, we always think of complex signals. So this real signal actually needs two. So this real frequency actually needs two complex exponentials. Yeah. So whenever you see omega naught as a frequency, you should always imagine omega naught and minus omega naught because you will need two exponentials. So that's you will always see two frequencies. Yeah. But again, you have these deltas, right? So can you now tell me? So it's now confirmed that essentially one real frequency is used, the other is just because of the exponential. How will this picture change in continuous time Fourier series? Can you quickly tell me? And then if we can reconcile this picture with the one in Fourier series. So in Fourier series, if I start with cosine omega naught t, right? I don't even need to compute anything. I just write the Euler formula. So what do I get here? This is one term, and the other one is
e⁻ minus iota omega naught t.
so if you think about this, this is already in that form. What is the form of the Fourier series? Right? Over all possible values from minus infinity to plus infinity. Why do I say that it's already in that form? I don't need to compute anything. Because this form tells you that you need combinations of exponential. This is a combination of exponential. But you just need two terms. All the other terms are zero. Yeah. So in other words, I can simply say that if I want to write a formula for CK, it is, can you tell me from this equation what CK is 1 over 2 when K belongs to, remember K here is 1, right? And here K is minus 1, right? So when K is minus 1 or 1, CK will be 0. Elsewhere or otherwise, it is 0. So how do you plot it? Hmm? Plot the signal in time domain. And now plot the spectrum in frequency domain, right? CK. What do you get here? Hmm? Sorry, this will be K. What do you get here? When K is 1, the value is half, right? When k is minus 1, the value is again half. Elsewhere it is again. Does it make sense now? And can you now connect it with that plot? Do you see the connection? The same picture. It's just instead of k there, if instead of k you had the labels were k omega naught, which will be your definition of omega k, then this one would be 1 omega naught, and this minus 1 would be minus 1 omega naught. And there you saw this thing 1 omega naught and minus 1 omega naught. And because, so here we are looking for actual coefficients, those coefficients are finite, yeah, half. But in transform, these become densities, and the density takes the form of Dirac delta. And this makes perfect sense because Fourier transform, the traditional Fourier transform or the conventional Fourier transform or the classical Fourier transform, whatever name you use, is meant for aperiodic signals. And this constant signal and this cosine signal is not aperiodic, it is periodic. That's why it will not converge in the usual sense. So you need generalized transform, and the generalized transform uses these generalized functions, the Dirac delta, but they remind us that, okay, in the Fourier series, it was a very simple thing, right? So what you can learn from all of this, if you have understood this, I can now tell you a very quick connection with probability and statistics. Yeah. So I suppose that Dr. Shizad Salim has taught you so far in random variables. He has taught you PMF as well as tell me P D
DF.
PDF, right? And I told you that PDF in a continuous random variable, the concept of PDF is needed because the PMF becomes zero, right? Just like these coefficients are only non-zero when you are dealing with periodic function, but the moment you apply a Fourier series to aperiodic functions, all the coefficients collapse to zero, and that's why you have to replace them by densities, and that's why you need transform. So a similar picture is here. When you are dealing with a discrete random variable, right, the PMF is, yeah, zero somewhere in non-zero. You still have some non-zero PMF. But if you apply that same concept of PMF to continuous random variables, all the PMFs become zero, so you have to replace them with densities and you get PDF, right? So now, just like we saw this connection, that if we now try that transform, in other words, density with periodic, and it was not meant for periodic, then you, instead of finite coefficients, you see deltas, yeah? So if I now ask you to give me the PDF of a continuous random variable, that will be usual, that you will get some plot, yeah? You have a continuous random variable, the PDF will be something like this. But if I ask you for the PDF of a discrete random variable, right? Discrete random variable is just like the periodic function in this course. So you should be, the first thing you should say that, okay, for discrete random variable, you should be asking me the PMF. Why are you asking the PDF? But I say, no, I do need PDF. So then you should expect those deltas, right? Because PDF was not meant for discrete random variables and you are still using it. Can you see this connection? If you don't see it, then you open your notes and then think about it, okay?
Yes.
Okay. I just want to give you a hint. I mean, we're not required to get into to depth in that direction. So, okay, let's go back to that table, and I want to um, deal with a few more things. Okay, let's try to work these two out. Okay, I'm now removing certain things. So we need to work with this thing, this one. Okay, although this is trivial, but I when we work this out, you will see something which is not visible just by looking at this formula. So let's say we want to remove all the notations. Sorry. So say we are interested in our signal x is exponential minus at u of t, and the requirement here is that a can be any complex number, uh, but the real part of that complex number happens to be positive. And at this point, you don't even need understand the condition why it needs to be positive, why not negative, why not zero. So if we now, the task is to transform it. So let's work out the continuous time Fourier transform. So our x of omega will be, can you now give me the formula? We need to work it together. So it will be minus plus infinity. What do I get here? Hmm? What do I get here? Hmm?
Minus iota k omega t.
Minus what? Minus j. We typically write
Omega
j, yeah, omega t
d.
dt. Okay. So u, we know u is 0, right? When t is less than 0. So the limit will actually be from 0 to infinity, yeah? Because u is 0 before 0. So u will be 1 in this region, and let's gather this thing. So it will be minus a plus j omega times t. Are you fine so far? What can you
Yes.
do now? Try your calculus thing. Do you remember how to work this integral out? Which rule do you need here? The power rule, right?
Minus a plus iota omega.
And this will be from, okay, what do we know now? What is the meaning of this symbol? Do we simply plug these values?
Yes.
Not in general. This is a very There is a common misconception. When we use these symbols, um, we because we are looking for convergence. So the way calculus has been developed, this actually means limits. And normally we are dealing with continuous functions, so we never see the limit. In a continuous function, the limit at a point is numerically equal to the value of that function at that point. So when that is not the case, then you will have to see limits. So actually, this means limit. Okay. So we have to. So I will still write that thing, but you must keep in mind that we are dealing with limits. Yeah. So I'll simply say minus a plus j omega t divided by, let's use that 1 over minus a plus j omega common, and here I am using this quantity, and I'll just write infinity here, right? I'll simply say t equals to infinity, and by this I mean the limit, right? I don't want to write this limit t approaches infinity, so think of this as a shortcut for the limit, and this one will be, which of these limits is straightforward to compute? Hmm?
Infinity 0, Jaya.
No, there is if it was so simple, I would never have done it this way. Yeah. So let's start with things that are easy. This one we know is easy, right? So because when you apply this limit t approaches 0, then I don't care whatever the value of a or omega is, as long as it's a complex number, I don't care, right? So it will be, what will be the value on this side?
1.
1. This will be 1, right? Without any condition. But here you have a problem. You say it will be 0, right? Because you see this minus t. So your thinking process is like this. Yeah. But here is a problem. You are only relying on the minus sign, but you are not looking this a at this a. This a in general is a complex number, right? So if a is a complex number, think uh, write this as a complex number. So let's say it is in this form. A is equal to, let's say, mm, a real and a imaginary, right? So let's say AR is for real part and AI is for imaginary part, and this is J, right? So what do I get here? I'll have exponential minus A real plus J A imaginary plus J omega, right? And I want this thing, this limit. Think of this as a limit. Do you now see the problem? Which of these terms matter for this limit? Hmm? There are three terms here, yeah? Which of these are important for this limit? I can even combine them into the imaginary, yeah? So J of AI plus. Actually, you know that the imaginary exponent has no role in convergence, right? Because it keeps oscillating, yeah? Actually, I would not say it has no role in convergence. It will not converge, right? So let's say this AR was 0. I'm just removing it. If this AR was 0, what does this thing mean? Forget about this infinity for a while. This simply means that it will be a complex exponential, yeah? It will have a real part and it will have an imaginary part, you know? Complex exponential will have cosine as the real part and sine as the imaginary part. Both are oscillating and they are oscillating forever. So how can you say that in the limit, now apply the limit, yeah? That in the limit they will converge to a value. How can you say that they will converge to 0? Can you say that? Hmm? So this does not converge to 0. It does not converge to any value, in fact, if this is only imaginary. Do you see the point now? The only way this thing can converge is if you have some real part. What if that real part is positive? Let's say this real part is positive. This negative multiplies the positive, this overall thing becomes negative, and now you have a decaying, because this complex sinusoid now gets multiplied by a decaying exponential, right? So instead of a perpetual sine wave, you have a decaying sinusoid. We don't need to care about negative time because negative time is zero anyway. Yeah? We have to thank you for that. So we don't need to worry about times before zero. We are only worried about times which are positive. In positive times, this positive real part multiplied with the negative will help this signal to converge to zero. Both these cosines and sines, which are parts of the complex exponential, they will approach zero. So now you should understand why this condition was given. The real part of A must be positive because then this u of t, this u of t getting multiplied by some signal which has a real part of the exponent positive and with this negative sign, actually multiply this with a decaying exponential and this overall signal will ultimately die down. Is that clear now? So what is your final answer? When we apply that condition that real part of A is positive, tell me now the final answer. This will be 0 and this will be 1 and this minus and minus cancel out and the final expression you have is A plus j omega, right? So let's summarize this. What we discovered is that exponential minus at u of t, which in the time domain will be not this signal but some, we can still use this dash 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 and it will be some actually decaying signal. For simplicity, let's say A is real. You can think about the imaginary part later on. So here the continuous time Fourier transform will be 1 over A plus j omega, right? And you can even plot the it will be x. So if this is x of t, this will be x of omega, and you can even plot the magnitude and the phase, the angle. Yeah, you can always write this in the polar form. Yeah, in the polar form it will be, you can always convert this into polar form. It will be a squared plus omega squared all square rooted, and this will be exponential because it's in the denominator, so it will be minus exponential minus j, and this will be actually arctangent omega divided by a, and actually this arctangent will not work. I mean there is this 2 argument. Yeah, if we had some values we could have worked this out. I told you that the arctangent will not give you the correct value every time, so you have to adjust it to the four quadrants, right? But anyway, you have this expression. So if I now ask you again, what made this transform converge to this expression? What was the reason? You need to pinpoint that reason before I move on to another example.
Real greater than 0.
Yeah, so 2 things help us. One is u, it was only for positive times, and because that was the only thing that mattered, and then the real part of A helped us. Okay, so now let's remove that. Let's remove that. And this is what I asked in that on GCR. I had this question. So if you now say, let's say A is 0 or the limit A approaches 0. So if I now start with this, I know exponential minus at u of t transforms to 1 over A plus j omega. And I say, okay, what if I set A to 0? Or I would say limit A approaches 0. So what happens to this side? u of t, yeah? And what happens to this side? 1 over. So can't we say that we discovered the Fourier transform of the unit step function? What is wrong in this reasoning? This was the question on GCR. Hmm? We know this is wrong, yeah, because the table of transform pairs doesn't have this thing. There is something else there. But from this limit, if we apply this rule, we get a simple answer. So why is that simple answer not available in the properties? What is wrong in this reasoning? Tell me now. Hmm? I asked you for the condition. What was the condition for this? Hmm? Real part of
सर
A is?
यूनिट स्टेप पॉजिटिव टाइम में होना चाहिए
No, real part of A. Real part of A is
ग्रेटर देन 0
greater than 0. And what are we doing here in this limit? We are making A 0. So when we are making A 0, we are making the real part 0. So then this whole thing collapses. This is not allowed when A is 0, right? So any conclusion you draw from this is actually wrong. So you need to read the condition carefully. Otherwise, you will try things which will computationally be fine, but conceptually they will be wrong. Is that clear now?
यस सर
So that now raises a question. How do we work out the transform of u of t, right? But for that, let's let's recall something else. So one thing is clear that because u of t does not converge, the transform of u of t will not converge. Yeah, because if we go back to this integration, and if we set a to 0, I told you when you set a to 0, then this will not work. So you cannot use integration because, and then you will need the generalized Fourier transform. So the only way you can write the transform of u is to have the generalized transform. The traditional transform will not work. Okay, generalized CTFT. But how? Before that, we need to recall how we worked out the transform of the signum function. Why I'm interested in signum? Because signum function has a very simple plot, which is 1 here and -1 here, right? And u of t can be constructed from signum function. I can write u of t as can you modify this signal to get your u of t? What transformation do you need to go from this signal to that signal? Hmm? You need to translate it vertically, yeah? So that you translate it vertically so that this -1 becomes 0 and this one becomes 2. And then you divide everything by 2. So I say, okay, I will start with signum of t. I will translate it vertically, right? And then divide everything by 2. So that will give me u of t. This formula will have one problem, right? It will have one problem. What is, so normally this should give me the correct answer, yeah? This should give me 1 here and 0 here. The only problem is the value at 0. The value at 0 here will be 1 plus sine of 0, which is 0. It will be half. But the way we have defined our u of t, we want to have value 1. Why does this not matter in this calculation? We don't care whether the value at 0 is 1 or half, because we will be integrating, right? In Fourier transform, we integrate, and the integral of this point will be 0 anyway, so we don't care, right? In transform calculations, these individual points don't matter. Whether I take 0 or half or 1 doesn't matter. Even if I take 2, it doesn't matter. The area is 0 there. So we'll still go with this one. So let's write u of t again. So it will be half plus half signum of t. We know from some previous calculation that the transform of 1 is 2 pi times delta of omega. So the transform of half will be half because it's linear. So the transform of half is pi delta of omega. So now we can easily say that the transform of u, Fourier transform of u of t, will be the Fourier transform of this, which is pi delta of omega, plus half the transform of signum of t. So all we now need is to work out the transform of signum of t. Okay, so let's start. Of course, signum of t is also not so easy. So I can give you a very quick way. This is signum, this is time, and this is signum of t. Let's plot it. 1 minus 1. This half we do later. So working out the transform of signum is not easy, but we try something else. Let's work out the differentiation. Let's differentiate this, and let's see if we can get something. So what will be the derivative of this function? I told you how to do that. What is the derivative of signum of t? What is the derivative in this region? Tell me quickly.
0.
0. What is the derivative in this region?
0.
0. What is the derivative in this region?
Delta.
Delta.
Delta. But you forgot something. That was the case for you, right? I told you that when you said delta, what is the area under delta?
1.
And that one
Infinite.
was justified because the integral was 1. You know, when you go back, you integrate. This jump is twice from -1 to 1.
2 of delta.
It's 2 delta. Now you are getting it, okay? So just writing infinity is not enough. But you know the transform of 2 delta. What is the transform of 2 delta? The transform of delta is 1. So the transform of 2 delta will be 2 times 1, right? So now you recall the property. What is the property? That if x of t has a transform x of omega, what is the transform of the derivative? We learned this property last time, right? Now apply this rule to this case. Set x of t to delta, to signum, right? So if I say if x is equal to delta, it will be, no, sorry, not delta, signum, right? If x is equal to signum, what is dx over dt? 2 delta, right? So what is the transform of 2 delta?
2.
2. So 2 equals j omega x of omega, which is the transform of signum, right? So what is the transform of signum? Two over, got it? We worked it out indirectly. It was not easy to work out the transform directly. We differentiated it. We got a simple. That is the strategy for solving these tricky problems. You try something and maybe you get a simple transform pair, and then you use the property. So we now know that the Fourier transform of signum is 2 over j omega. And now let's get back to that. We now can attack the Fourier transform of u. So what is the Fourier transform of signum? We just worked it out. 2 over j omega.
Iota.
And 2 cancels out, and your final expression is 1 over j omega. So now our reasoning was half correct. We did expect 1 over j omega, but because of that convergence issue, that one term was missing, and the generalized transform helped us fill that gap, right? So remember, this is something you could have done without generalized transform as before, but this part only is made possible by generalized Fourier transform. Is that clear? So write P in the chat window, right? Because we are close to the end. If there are any questions, we can have one question. But don't think that what I did in the lecture will be enough. Okay, we cannot solve all the questions. We cannot make all these connections. So I will highly encourage you to look up in the textbook, pick randomly examples from the exercise or uh, from the main chapter, and try to find these connections yourself. You're capable of doing that, right? So my job is only to give you that direction. Don't expect all the questions to be solved in a classroom. So okay, we can close now. Thank you.